Hello and welcome to this bonus video here where we are going to go through some of the calculations that we weren't able to get to in lecture today. And so what we wanted to focus on here was just, again, reviewing some of the calculations involving electronic transitions and the light that comes from those transitions to help us better understand what's going on inside of atoms when they make these atomic spectra. So we saw in lecture today this example where we use the energy of a photon and its wavelength, and we figured out its energy. So what we want to do now is we want to see how we can go about doing this further. So very similar kind of question here. Only difference is that we are not interested in the number of moles this time, but we're going to calculate the actual energy in kilojoules. So we have a wavelength of light of 514.5 nanometers. We want to convert that into kilojoules of energy. So if you remember from the previous slide, we took our two energy equations and we set them up so that we could use one to solve for the other. So remember, we turned this one into an approximation for frequency using wavelength and the speed of light. And then we substituted it in. So our equation here is energy is equal to Planck's constant times the speed of light over the wavelength of light. And so we're talking about 6.626 times 10 to the negative 34th joules times seconds, multiplied by the speed of light, 2.998 times 10 to the 8th meters per second, divided by the wavelength of the light, 514.5 nanometers. So 514.5 nanometers. Remember, we're going to do a quick cheat on this. To turn the nanometers into meters, we're just going to apply the exponent 10 to the negative ninth. So even though that this is not proper scientific notation, it is good enough for our calculator to use. So 514.5 times 10 to the negative 7th meters, or excuse me, times 10 to the negative 9th meters. And so we plug that into our calculator. And we get an energy value. And this energy value is going to be in joules because our seconds cancel out and our meters cancel out. So we're left with just joules here. So our energy value here in joules, 6.626 times 10 to the negative 34th, multiplied by the speed of light, 2.998 times 10 to the 8th, divided by 514.5 times 10 to the negative 9th. Four significant figures this time because we have four digits in all of these numbers. It is 3.861 times 10 to the negative 19th joules. Now, if we compare that number of joules to the number of joules that we had for 640 nanometer light, we do see that this was 3.10 times 10 to the negative 19th. This is 3.86. So this is more energetic, which does fit into what we were talking about in our previous lecture, the fact that green light is more energetic than red light being the light that we saw in the previous example. Now, it doesn't seem like a ton, but it is definitely enough to notice. And when we start to look at things from the photoelectric effect standpoint, that extra amount of energy could be the difference between an electron popping out of the atom and staying in the atom. Now, we're not quite done because we need to turn this into kilojoules. So one more conversion is necessary. There are 1,000 joules in 1 kilojoule. So the correct answer here, 3.861 times 10 to the negative 22nd kilojoules. And that would be what you would need to put into top hat if you have not done already. So, and again, E for scientific notation. So this would go into top hat 3.861 E negative 22 would be the value that you put into top hat. So that's this second calculation. So again, it mimics that first calculation. It's the same kind of calculation up until this point. In the first one, we then turned it into joules per mole. So the second conversion there was multiplying by Avogadro's number. In this conversion, it's turning the joules into kilojoules, which is something that we should already know how to do. So we want to move on to the next piece of business, and that was we were looking at line spectra. So we looked at the idea of emission spectra, and we said that we could calculate the energy of these lines using this equation here, where negative r times this subtraction of fractions would give us the change in energy. Now, the change in energy here, again, very similar to what we saw with light. A positive value means that energy goes in and the electron goes up in energy level. And a negative value would mean that energy is going out, and so that the electron must be going down in energy. And so we used similar kinds of argumentation. We used similar kinds of argumentation when we were looking at this originally and talking about wavelength. So our questions involving calculations here are, how do we come up with these numbers? How do we come up with these energies? And so the first one is asking us for the wavelength in nanometers of the line in the spectrum that gives us this energy transition. Since we are talking about wavelength, we need to use the version of the equation that is going to give us that wavelength. And that's the Rydberg equation. Which again, we saw the Rydberg equation previously when we were looking at this for the first time on Wednesday. In order to use this properly, we had to use this value of R. So R in this case is 1.097 times 10 to the 7th. And that unit is wave numbers. 1.097 times 10 to the 7th wave numbers. So that's meters to the -1 power. We're going from the 4th level to the 2nd level. So our final destination is the 2nd energy level. So that's going to be our F. So 1/2 squared. Our initial was 4. So 1/4 squared there. So if we do this calculation out, we've got 1/2 squared, so that's 1/4 minus 1/16. So 1.097 times 10 to the 7th reciprocal meters is equal to 1/4 minus 1/16, which is numerically 0.1875. So 1 over the wavelength is 0.1875. Times 1.097 times 10 to the 7th. And when we do that, we get to 4 significant figures. 2.057 times 10 to the 6th reciprocal meters. Now, this is not a wavelength. This is 1 over a wavelength. So what we need to do is we need to take the reciprocal. We need to flip this fraction. And so to do that, your calculator either has a 1 over x button or a negative first power button. If I do that, this flips this fraction. So from 1 over lambda to just lambda. 1 over 2.057 times 10 to the 6th reciprocal meters is 4.862 times 10 to the negative 7th meters. To turn the meters into nanometers, we need to apply our conversion. So dividing by 10 to the negative 9th, we get 486.2 nanometers. And so since this involves a transition from the 4th level down to the 2nd level, we are going to see light being emitted here. And so that's what this is telling us. Light's coming out of this, and the wavelength of that light is 486.2 nanometers. Now, if we were going to look at this further, let's say that we were asked a question about energy instead of wavelength. We could use this equation just the same, and it would give us basically the same outcome. So just as kind of a point of comparison here, let's take a look at that. I'm going to do that in a different color here. So let's do that one in light blue. Delta E is equal to negative 2.18 times 10 to the negative 18th. Joules. And we've got the same transitions here. So 1 over 2 squared minus 1 over 4 squared. Luckily for us, we've already done that calculation. So negative 2.18 times 10 to the negative 18th joules times 0.1875. So delta E would be the three significant figures, negative 4.09 times 10 to the negative 19th joules. And again, what does that negative mean here? It means that the energy is being lost. It's being displaced. It's coming out of the atom instead of going in. So that's what the sign means in these kinds of cases. For wavelength, we don't worry so much about the sign because there's no such thing as a negative wavelength. But for energy, we're looking at things from an input and output standpoint. Positive means that energy went into the atom, and so that means that light was absorbed. Negative means that light was being pushed out of the atom, and so we see light being emitted there instead. All right, so for the last one here, this last bit, we're going to actually need to go to top hat for this. And so in top hat, you have this question. All right, so we're looking at the question over here. And the question over here asks, which of the following transitions is the most energetic and which is the least? So the way to answer that question, the thing that we have to think about and know is, let's put the possibilities here. We've got n equals 3 to n equals 2. We've got n equals 4 to n equals 2. And we've got n equals 5 to n equals 4. So if we're looking at these three possible transitions, what we have to think about is, let's go back to this diagram here. And the thing that we should notice in this diagram is that as we get further away from the nucleus, so the first energy level, the second energy level, the third one, and so on, as we're getting further and further and further and further away, the energy levels are getting closer and closer and closer and closer together. So with that in mind, we would have to know that this energy transition is going to be the least energetic. And the reason it's going to be the least energetic is because as we go up and up and up and up and up, the energy levels are getting closer together. So that means that these two energy levels, 3 versus 2, are going to be further apart in energy than 5 and 4 are. So 5 and 4 is going to be the lowest in energy of this group. Now, between these two, it should be pretty easy. This one's jumping 2 energy levels. This one's jumping only 1. So this one has to be the more energetic one. And this one has to be kind of in the middle. Again, the reason we know this, the reason we can rationalize this order is, the more transitions that are made, the bigger the jumps are going to be. We saw a version of this again in that diagram that we had, where we can see that within a given series, a 2 energy level jump is going to be more energetic than a 1 energy level jump. But a 3 and a 4 energy level jump is going to be bigger than all of those. But what's also important here is that notice that all of the energy jumps in the Lyman series are more energetic than any of the ones in the Balmer series, even the one from 2 to 1. Why? Because the gap between 2 and 1 is bigger than the gap between 3 and 2. And all of the Balmer series lines are bigger in energy, have smaller wavelengths than the Passion series. Why? The gap between 3 and 2 is bigger than the gap between 3 and 4. So any of these kinds of transitions are always going to be depleting in magnitude. As we get further away from the nucleus, the energy levels get closer and closer together until eventually they become so close together that they really aren't distinct energy levels anymore. We call that the infinity level. And at the infinity level, when we get to that spot, that's kind of considered the outermost reach of the atom. When an electron goes beyond the affinity level, well, that's when we no longer consider that electron part of the atom. That's when we talk about things like the photoelectric effect, where we have something happen that tells us that the electrons are no longer there, they're gone. So that concludes for us this little recapping and walking through some of these calculations and going in through Top Hat. Again, when we pick up with this on Monday, we're going to be talking about the concepts of kind of the grand summary of what all of this leads us to, and that is the quantum mechanical model. And with the quantum mechanical model, we'll also very, 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 very briefly talk about something called the Schrodinger equation and how it leads to a re-understanding of the Bohr model of the atom. It helps correct for some of the Bohr model's faults, which are actually more numerous than you might think. So that concludes this particular side lesson. Thank you for tuning in and paying attention, and I will see you in class.